Is it starting? Yes, right? Okay, perfect. Okay, good afternoon. Welcome, everybody. My name is Estefania Gonzalez, and I'll be your host today. I would like to welcome you to our webinar, Bioimpact. And why bioimpact? Well, because we're celebrating 2 years of innovation in our biomethane production with SEMPRE-BIO. SEMPRE-BIO. There's two ways of saying it. So we will start shortly. Get comfortable. We're just going to wait a few seconds. Like normally people take like 1 or 2 minutes to get into the webinar. So in 2 minutes, we'll start. Okay. Everybody is coming in. Perfect. I just want to remind everybody that this webinar, it's being recorded and it's also being transcribed. During the Q&A session, you can participate by typing questions in both the chat or the Q&A button that you have in the top of the screen. If you prefer, you can also raise your hand and I'll give you permission to activate your microphone and your camera, and then you can ask the question directly. Just a reminder, if you want to proceed with this, we are recording, so your image is going to be storage. We have the GPD in Medium, and I'll put the link because this webinar is being organized from the Medium group Teams platform. Okay? Vale. We are letting people in. Perfect. 30, 40. Let's. Well, we're all really excited to start. Perfect. Okay. So just before I begin, once again, this webinar is being recorded. So please have this in mind whenever you want to participate. Okay. So here is what we have planned for today. First of all, this project is funded by the European Union, and we cannot forget about that. So today we are going to start with an overview of the project SEMPRE-BIO, and it's going to be presented by Alejandra Cordova, our project coordinator from Cetaqua. Then we will have the 3 case study presentations. The first one done by Checa from Cetaqua also, and he will present the first case study. Following that, we had a last-minute change. Arthur Crane is sick and he could not join in today, but don't worry about it. Andrea Munaretto is gonna, David is gonna present this second. Well, we're gonna see him during the first one and the second. Next, we're gonna have Andrea and Çagri from Ghent University and Andrea from Fiorentini will present the third case study. And afterwards, we're going to have Georgina del Puerto from Beta Technological Center and Marcella Souza from the Ghent Universiteit, Ghent, and they will discuss the CO2 valorization. Lastly, we'll have a Q&A session where you can ask our presenters any questions you may have. Again, this can be done throughout the chat that we have or the Q&A. Also, if you want to be in camera and do the question directly, you can raise your hand and I'll give you access to, I'll activate your microphone and your camera and you can do the question directly. Just as a reminder again, we are recording this, okay? So let's begin. Just as I was mentioning, our first presentation is going to be the overview of SEMPRE-BIO by Alejandra. So Alejandra, the floor is yours. Please go ahead.
Thank you, Estefania, for the introduction. Let me share my screen. Okay. You can see it properly, right?
Yes, we see you.
Okay, thank you, Stefania. Well, thank you for the introduction. Good afternoon to everybody. My name, as Stefania mentioned, I'm Alejandra Cordova, project manager at Cetaqua, and also the coordinator of the SEMPRE-BIO project. Well, let's start with our project. First, what means SEMPRE-BIO? SEMPRE-BIO is the acronym that stands for Securing Domestic Production of Cost-Effective Biomethane. And the objective of this project is to demonstrate these novel and cost-effective biomethane production solutions and pathways that are essential for the 2030 and also for the zero emissions from the 2050. Also, to increase the market acceptance of the technology related to biomethane, of course, supported the circular economy and also to reduce the dependence on fossil fuels. The SEMPRE-BIO is a 9.9 million euros project funded by the European Union under the program of the Horizon Europe. It is a 42-month project that started on November of the 22 and will end in April of 2026. It's made up of 7 countries. In this case, it's Spain, France, Belgium, Germany, Denmark, Norway, and the Netherlands. And is integrated by 17 partners with different expertise from various sectors across Europe. Each of our 17 partners bring in a unique capabilities and also contributions to the stable. So first, we have in the research organizations, we have a strong support from the research institutions such as DBFZ, SINTEF, INNOLAB, and also Cetaqua, which is the coordinator of the project. Also, in our industrial partners, we have to include Aguas de Barcelona, Crioinox, Propulse, TerraWatt, and Biomethane. In the academic institutions, we have DTU, the Ghent University, the Beta Technology Center that bring the academic knowledge to the project. Our end users partners are like TMB and Naturgy, with BB is essential in adopting and scaling the biomethane technologies that we are developed into this project. Invenian as our consulting partner, Biogas E as the stakeholder engager. And finally, we are collaborated with farmers. In this case, is the NB, the Sauenbloen, who are integrating implementing the biomethane solutions in the agricultural level. Through the combined efforts of these 17 partners, we aim to advance the biomethane production and enhance this resource efficiency and to contribute the European energy transition. Here we can see 2 slides that represents like the biogas production from in the 2022 in the image in the left that was almost exclusively based on anaerobic digestion with biogas dominating the market. So the potential for growth is projected to increase slightly by the 2030 with also anaerobic digestion remaining the primary production method. But we are going to have a further significant growth that is anticipated toward the 2040 and the 2050 with both anaerobic digestion and thermal gasification playing important roles. In the case of the thermal gasification, it's expected to become significantly more relevant in the 2040 as this technology is increased and mature and also being more commercialized. In the other hand, in the image from the right, we can see that by the 2040, Europe is expected to have like a biomethane production potential of 111 billion cubic meters per year, supported by these 2 main technologies that I already mentioned. The anaerobic digestion from one side with 67% of the total, and with the thermal gasification with a 33% of the percentage of the total. The countries with highest potential are Germany, France, Spain, Italy, and the United Kingdom, which these both collectively account like a 50% of the Europe's total biomethane production potential. Also, we can see a high potential in Poland. In these 2 images, we can see like the breakdown of the feedstock and the technology selection that will drive the biomethane production in the 2040. First, we can see that in the anaerobic digestion for the 2040, that it will have a potential of 74 billion cubic meters per year. The main feedstock here includes the sequential crops, Then is followed by the agricultural residues and also with the animal manure. And together with these three different feedstock is almost account the 82% of the total feedstock for this technology. Another important source here to mention is that we have to include the industrial wastewater that it contributes with 11%. Here, the top 5 countries are Germany, France, Spain, Italy, and Poland. And from the other side, from the 2040 regarding the thermal gasification, we can see that the primary feedstock are wood waste with a 32%, municipal solid waste, forestry residues, and which together of these 3 feedstocks, it's like around 85% of the total. Here, the top 5 countries are Sweden, Germany, Spain, United Kingdom, and France. And if we go now into the SEMPRE-BIO again, in the SEMPRE-BIO, we established the 3 European biomethane innovation ecosystem, as we call it, the EBIs. And these are like the representative of the different biomethane production across Europe. So this will be in these 3 cases of studies. In the case study number 1, that is in place in Spain, the case study number 2 in France, and the case study number 3 in Belgium, where 5 different technologies will be tested. And these EBIs will facilitate us like a long-term replication, creating an active flow of information, and this information will create future investment opportunities. Let's make a brief summary of each of these case studies. In the case study number 1, that is located in Spain in the Baix Llobregat wastewater treatment plant that is operated by Aguas de Barcelona, we are going to demonstrate an innovative combination to produce biomethane. That the aim here is to valorize the current biogas stream by converting it in biomethane by using a novel combination of the electrolysis of water and the CO2 biomethanation. The produced biomethane will be stored for then subsequently used in the buses in the Barcelona's public transport system. So this initiative showcases like an environmentally friendly approach to waste management and renewable energy production, while simultaneously we addressing like an urban transportation needs. In the case study number 2, that is placed in Bourges in France, it will produce biomethane from non-digestible urban green waste. So a pilot here will produce biomethane operating with wood biomass and organic biomass from the city of Bourges. And the innovative conversion will be with the combination of also 2 technologies. Here we are going to use the pyrolysis and the methanation to produce biomethane that then will be injected into the network using the existing facilities. And finally, in the case study number 3, that is placed in Ghent in Belgium, here address some challenges because it's placed in a farm with low biogas production and no natural gas connection. So this make like a small biogas production and not be sustainable and profitable. So the project here will demonstrate that these novel solutions focus on biogas purification and liquid biomethane production is possible. Here we are going to use like the cryoseparation process, the cryoseparation technology, and the plant will produce from one side liquid biomethane for local storage, and then we are going to explore with the liquid CO2. We are going to explore to valorize with some methods to try to produce different products such as proteins or polymers. And the main objective here is to showcase the potential of the small-scale operators creating a viable model to decentralize the renewable energy production in rural areas. In the subsequent sections of this webinar, my partners will provide you more detail and explanation of each of these case of studies. Now I want to present this slide because this provides a quick snapshot of where we are in terms of the overall progress in this SEMPRE-BIO project. We are at the 57% of the way through the project's timeline. So far, we have completed the 50% of the milestones, and these are key achievements that we have been planned. We are on track in terms of reaching the other 50% that expected from the milestones for this project. In terms of deliverables, we have completed the 44% of the outputs promised for the project. This includes reports, results, and other formal of outcomes. And finally, the project tasks are currently on the 18% of the completion. And this shows that there are still some significant work ahead in terms of individual tasks, but this is aligned with our schedule. We are making a steady progress all across all of the areas, so we are confident that the project will continue to meet the objectives and move towards to the next phase. I want to present here some of the expected results for this project. The first one is to increase the cost effectiveness of the conversion in biomethane production. And this is through the optimization of the biomethanation production, with economy of scale in biogas, also with upgrading in small plants, increasing the type of the volume and the different raw materials from the different scenarios that we are working here in these 3 case of studies. The second one is diversify the conversion technologies for biomethane. And here, because of the 3 case studies that we are going to test a variety of technologies, in specific 5 different technologies from different raw materials that are kind of unrepresented now in the biomethanation, in the biomethane production, like that show a high biomass potential. The third one is to contribute to the acceptance of the biomethane technologies in the gas market. And this will be thanks to the techno-economic study that it will be integrated in the 3 case of studies. That is really an important tool that it will be really interesting for our stakeholders, as well as the experience of our public and private sector of the EU, of the 17 partners that make up this consortium. And finally, to contribute to the demonstration of the semi-industrial scale of the new conversion technologies to produce biomethane from wastewater, wood biomass, and manure. Finally, to finish with the introduction of this webinar for this project, is like the expected impact that we are planning to have is like having a more efficient, cleaner, and sustainable energy source, as well as safer. So here we have some bullet points. Here is like the biomethane as substitute for the imported liquid natural gas. So we know that biomethane has a calorific power equivalent to natural gas. So this is ideal to replace this with biomethane. Just a number that I can give you is that, for example, in the 2020, 81.6 million tons of liquid natural gas were imported. So the idea is to replace like around of this 30% in line with the EU 2050 targets. The other one is biomethane as a fuel substitute in transportation. So here, if biomethane, specifically liquid biomethane, reaches competitive prices, it would be like a good idea to use to replace the transfer fuel, substituting the oil-based fuels, reducing this primary energy demand. The other one is the reduction of the CO2 by 13 million tons years by the 2050. Also diversify the energy sources and these new routes. And this is really specific because we are trying to reduce the dependence on fossil fuels from foreign producers through local production biomethane. The other one is reduce the needs for the strategic reserves and also the smaller extension of critical infrastructure to protect. And this is by promoting local circular projects with short distance between the gas production and the consumption, reducing the surveillance of kilometers of pipelines and also in the infrastructure that is needed to transport this gas. Thank you for your attendance. I give the floor to the next participant.
Thank you very much for your presentation, Alejandra. So now we have David Checa from Cetaqua also, and he's going to talk us about it, the case study number 1. David, over you.
Great, thank you. So I'm David Checa. I also work at Cetaqua with Alejandra. I'm a researcher there, and well, I will explain you case study number 1. That, as Alejandra told you, this case study is placed in Barcelona. It is placed in the Baix Llobregat wastewater treatment plant that is currently operated by Aigües de Barcelona. So this case study, we use wastewater as their feedstock. This wastewater goes through a treatment, and after the anaerobic digestion, we get the biogas. This biogas has around like 35% of CO2, and with this CO2, we do a biomethanation. To do this biomethanation, we also need an electrolysis. But with this electrolysis, we produce hydrogen. So this hydrogen with the CO2, then we can produce the biomethane that is used in this case to run the buses around the Barcelona metropolitan area. So here, the electrolysis is done by Propulse, our partner in Germany. They design and they perform all the engineering for the PEMEL. And then the DTU did some studies in order to select which kind of reactor was the best one. And we will also do, well, we'll work, here is missing Biothane. We work with Biothane to do the design of all the plant. And finally, we will do a techno-economical analysis with SINTEF, and that will help to see one techno-economical analysis. So this technology, this whole concept is called power to gas. Here I've put an image of an abstract of a paper by Seaborg et al. And here you can see the whole concept of power to gas. Power to gas means that you have power like electricity, and you transform that is volatile, and you transform it into another kind of energy, in this case, a gas. So the idea here is because the renewable energy, sometimes there are peaks of production that do not match the demand, this energy is missed and it's gone away and no one uses it. So a way to store this renewable energy is to use it to produce a gas that can be stored. So how we do it is we take this energy and we run it through an electrolyzer. This electrolyzer takes water and splits the molecule into hydrogen and oxygen. Then this hydrogen, you can already use it for running buses, or it has already uses. But hydrogen is a very small molecule and it's very hard to store, and there is no currently an infrastructure. So what we do is use this hydrogen to produce another gas, in this case, biomethane. Biomethane is like 97% of methane and the rest are impurities. So in this way, we are upgrading this biogas that is 35%, 65% of methane to 97% of methane. And because the composition is basically the same as natural gas, we can inject it directly to the natural gas grid that it already exists, and we don't need to build a new infrastructure. This is why we are doing the whole biomethanation. So here is another abstract with more images. Basically, you need hydrogen, you need a carbon source, in our case it's biogas, and then you need a bioreactor. So in this bioreactor, we have microorganisms of a lot of kinds. Like you can have microorganisms that eat the CO2 and the hydrogen and produce methane. You have some microorganisms that eat CO2 and hydrogen and produce acetate. You have some others that eat this acetate and extend the chain, producing volatile fatty acids. You have some microorganisms that eat this acetate and produce methane again. So a lot of kinds of microorganisms. So we need to run this reactor in specific conditions in order to promote the growth of hydrocentropic methanogens that are the ones that will produce the methane. These are archaea. Well, these are the ones that the ones that we will use. So as I told you, this way we can produce biomethane, and this biomethane has various final uses. You can liquefy it to use as LNG. You can compress it like we do to 250 bars, and we then use it for public transportation. And well, the other uses that you can think of, you can inject it in the gas grid. So as a summary, this power to gas concept is taking electricity to produce hydrogen. Then this hydrogen, along with the biogas, you get the biomethane. So you can see here the anaerobic digestion, you produce biogas, but you also produce this digestate. So we use this digestate as the inoculum for the bioreactor. There are a lot of different microorganisms, and as I said, we run the reactor at certain conditions to promote the growth of hydrocentropic methanogens. Then the PEMEL, that means proton exchange membrane electrolysis, is the electrolyzer, in this case, designed by Propulse. An important factor of this is that we use it with regenerated water because especially in Barcelona, that there is a drought, we cannot use tap water because it has to be used for human consumption, not for producing fuel. So we use regenerated water. Another water source that could be used maybe would be seawater, but this kind of electrolyzers are way more complex. So, well, finally, I will explain which kind of design we use. So the DTU performed a study with various kinds of reactors. Among them were a constant stir tank reactor, a hollow fiber reactor, and a bubble column reactor, and a trickle bed reactor. So with their experiments, they found that the reactor that has the most production of methane is a trickle bed reactor because it maximizes the mass transfer. So this kind of reactor consists of 3 different phases: a gas phase, that is a biogas and the hydrogen; a solid phase, that is the packed material where the biofilm grows; and a liquid phase, that is a liquid sump at the bottom that we recirculate to the top, and we, with some showers, we sprinkle it on the bed so the bacteria are moisture and have enough nutrients to grow. So, well, you can see here that there is a liquid circulation that we can regulate. And with this, we can regulate the pH, the nutrient concentration, and also we can regulate the temperature. The temperature range we use is thermophilic because it's the one where the methanogens work the best. And there has been a lot of studies that show this, and this is why we use this. And we also work under pressure. We will use a range from 3 to 8 bars in order to see which one is the optimum one, because it's not clear, because yeah, the higher the pressure, the better, but also it is more expensive. So with SINTEF, we will do a techno-economic analysis, and this will be one of the points to see which is the optimal pressure. Then we will use high-density polyethylene pole rings as a packing material, although there are other options like clay materials that are also very interesting because they are more sustainable. But right now we would use pole rings, polyethylene pole rings, because it's the one we use in DTU, and we are sure that we'll have a good, well, they will work fine. So the flow that we will use is to treat up to 15 cubic meters of biogas per hour. And because the biofilm needs to be adapted, we will begin the operation slowly and progressively increase the gas until the 15 cubic meters that you see here. And finally, we need to treat this biomethane so it complies with a norm and we can use it in public transportation. So for this, we have to remove impurities like hydrogen, like sulfuric acid and siloxanes, and also other bugs. And we also have to correct the dew point so to comply with a norm, so it doesn't freeze in the engine. Well, finally, I can show you some picture of the construction advancements. Currently, the most advanced one is the PEMEL. The PEMEL is already under construction. Here you can see the container. You can see some vessels that are constructed specifically for this. And we already have all the equipment. This is being built in Valencia, and it hopefully will arrive in Barcelona by December, January, and to begin the operation in February. Then the biomethanation is a little bit behind that. We still are starting the detail engineering, and we think that for February it will be already be there, and we will have more advancement. Here you have also a picture of a bus. This is for another project with Cetaqua, a live project called Nimbus. And here you can also see the gas station that we will use. We will reuse this one because it's functional. And here you can also see the Life Nimbus project. It's a functional biomethanation plant. Here there are also the gas bottles you can see there. We will be also reusing that. And here you can also see the reactor. That this one is 6 meters close. On the left you can see the 3D model for the SEMPRE-BIO. This will be like 3 times bigger then the nimbus and the reactor, to give you a sense of scale, will be like 11 meters tall. And well, hopefully for December, we have more updates. And for now, this is everything. So thank you.
Thank you very much, David. I think we will continue with you, right? So that we can share now the presentation. Like, yes, as mentioned before, sadly, Arthur could not join us. So, David, back to you.
Yeah. I don't see my screen now. It's black.
Yeah, we also see the black. Oh, it comes and goes.
I don't know what happens.
Oh, now we see it. Oh, okay. When you share it, no, we only see black.
Yeah. So the
when
images.
I'm
reloading the page.
Okay.
Everything was working so smoothly.
Yeah, that's odd.
Well, I can do a presentation like this, or it's fine. Or...
No, I can share the screen. Oh, it's Georgina. Perfect. Yeah. Perfect.
So I'm not Arthur, as you know, but I will explain you case study 2. I'm not an expert on this, but I will do my best. So forgive me if I say anything wrong. You can correct me, but I think I can manage. So I will introduce it. So case study 2 takes place in Bourges in France. It's located, as you can see here in the map, in the Marmande Ecopole. Here they have an anaerobic digestion plant. They also have solar panel farm, and they have a lot of crops. So this is key because they will be using this bio-waste for the pyrolysis. There is also a gas grid injection point, so it is nearby, and we do not need to have a long, like it's not far away, it's right there, and it's a key strategic point. So this process consists of a pyrolysis followed by also biomethanation. In this case, it is not a CO2 biomethanation like the one I explained before. This case is a syngas biomethanation. So the syngas has hydrogen, carbon monoxide, and carbon dioxide. This carbon monoxide that is not in the biogas makes a lot of difference because there are even more microorganisms there that produce more parasitic reactions and makes the process even more difficult. So, well, this is a challenge for them. But, well, here the process, they start with body biomass, like you can see here that they get from the crops, and they treat it and they put it into a pyrolyzer. This pyrolyzer works like, I think, at 700 degrees Celsius or something like that. And there they produce syngas, and there are also bio-oil and biochar. These are byproducts that can be used that have other uses. But here we will focus on the syngas. This syngas then goes to, as I said, a biomethanation reactor where they produce biogas. So this biogas is not yet biomethane because the composition they get because of this carbon monoxide is lesser than the one we get with only biogas in Barcelona. So here they produce biogas and then inject this biogas into an already existing system that is the membrane separation. So this way they can produce that biomethane that has the quality to be injected into the grid. So here you can see that DTU also did work for the reactor, and also TerraWatt and Syntef will be doing the economic and the techno-economic evaluation. Well, this is what I just told. Biomass, and here you can see the biomass that they use. It's a woody biomass. I think it's not very humid because the biomass that enters the pyrolyzer doesn't need to be very humid. And also it needs a certain size, like it cannot be very big, so it has to be cropped down in the pretreatment, like you can see it here. It's 50 millimeter particles. they have to separate off the rocks, all the metals, so it doesn't damage the equipment. And like I said, they have us running on site with another project partner where they crop down the biomass to the correct size and like pelletize it, to say so, and then inject it into the pyrolysis. So this pyrolysis, as I said, is high temperature. In the beginning, the pyrolysis is not self-sustained, so they need to inject a little bit of fuel. So it starts up, and then once the pyrolysis process is already working, then it's self-sustainable. So just by burning the biomass, they are able to keep this temperature high, and because it's exothermic, they don't need to cool it down or anything. It's already high temperature. And moreover, they produce energy, like I said, the syngas, also the biochar and else that can be used for other purposes. Like it produces energy, so it's energy positive. Like I said, an external heating. Well, I'm not I think the pyrolyzer is just this rotatory kiln, and then through exterior runs the hot gas. And I'm not very sure on that. Sorry. Well, I will keep going on. Then the part that I know more of is this biological methanation. Then this syngas, they can already inject it into the biological methanation. And here they do it differently than in Barcelona. Here they do it with, well, it's not here. They use 2 reactors, not just one. And they use a really brilliant solution, and that I cannot explain well, so forgive me for that, but they use 2 reactors and yeah, they flood one while they use the other, and once and because they are flooding it, then there are more microorganisms there, then the production is higher, then they empty it, flood the other, and use the one that has just been inoculated, so the production is always the maximum. I think it's something like that. And well, yeah, here, as I told you, there are a lot of different reactions because there is also CO, like carbon monoxide, where it complicates everything, really. But well, here you can see also pictures of the units. And here is the work by DTU that they help selecting the reactor. Like I said, we use a biotrickling reactor. They also, with them, we also selected the metrics where the microbials work, grow, and also optimizing the parameters like the liquid and the gas flow. So selecting the correct gas residence time, the correct liquid recirculation rate, and well, they did a study on that. And then also optimize the biological process, like I told you, selecting the correct temperature. As I said, thermophilic temperature, 55 degrees Celsius. The kind of nutrients you can use either a natural source like digestate, or you can also use an artificial source that will be more specific for the process. And here you can see, as I told you, the bubble reactor and also the trickle bed reactor. The bubble reactor is full of liquid, and the gas flows through the liquid like bubbles. This is what is called bubble reactor. And here you can see the two reactors, like the 2 tanks. These are way bigger than in the Barcelona site, like 20 to 25 cubic meters or more on the top of my head. And in their case, they do already have the pyrolysis, the pyrolyzer. They have it on site. And they are waiting on the syngas analysis in order to progress, because they will design these 2 reactors depending on the syngas that they get. So the composition out of the syngas will be, they don't know it yet how it will be, and with that they will design the reactors one way or the other, and this is where they are working now. As you can see here, the liquid is trickling to the packed bed, and the syngas flows countercurrent to this liquid. And at the end, they have the biogas where it goes to the membrane, separates, and they have the biomethane. Here is a cool video of the 3D model. You can see here the pyrolysis kiln, the two bioreactors. They also store the biogas line here. And well, the radar must be around here too. You can also see the comparison with a person. And also finally this gasometer where they store the gas product. And here, well, like I told you, biomethane inhalation tank, the biogas output, this conveyor belt. Here they collect the biochar that I don't know what they use it for, but has many uses like in agriculture. They can also use it as an additive in construction materials like cement and many others. And also the pyrolysis kiln is run by SEMPRE-BIO, a German company. And this pyrolysis kiln here is by energy. And here is the hopper where they feed the bloody biomass that I showed you at the beginning. And here they store the oils and all the condensate. And I think this is everything. So thank you. I hope I explained it well. And I'm sorry that Arthur couldn't be here, but I hope I did it well.
Okay, thank you very much, David. It was really quite good, the fact that you could join in such short notice. Okay, so that was case study 2, and now we are going with case study 3, who will be presented by Çagri and Andrea. So, Çagri, the floor is yours.
Thank you, Estefania. Yes, I think you can see me and hear me. All right.
Yes, we can see you and hear you.
Okay, good. Third and final case study of SEMPRE-BIO. Downscaling biogas upgrading solution. Here, the aim is to investigate the potential and feasibility of downscaling a biogas upgrading solution, which is a cryogenic solution to produce bio-LNG and liquid CO2 from biogas at farm scale. The demo plant is located in Flanders, Belgium, more specifically in West Flanders, which is characterized by high agricultural activities, where most of the farming in Flanders take place in this region. And of course, in return, we have high amount of agro residues, manure being the most abundant and let's say most problematic one for this region, because due to these intense agricultural activities, we have excess nutrients in soils. So Flanders is considered one of the nitrate vulnerable zones in Europe. So that's why the soil application of manure and manure-derived digestate is limited to 170 kilogram nitrogen per hectare. That's why farmers need to seek and adopt solutions to deal with their manure. So talking about farms and manure, the demo plant is to be installed on a dairy farm, which has a biogas permit to process 25,000 tons of cattle manure per year, together with 5,000 tons of another co-substrate. Here you can see on the right side the farm from above before the biogas reactors were installed, and below some pictures of the reactors and the farm. So the digesters have been operational for about 8 months. We have 2 digesters working in series. The first one is a mesophilic digester, and the second one is a thermophilic digester, which acts as a post-digester. So they are processing manure from around 900 cows, together with other agro residues. And the resulting digestate is being transported to France to be used as an organic fertilizers due to the restrictions I mentioned. And regarding the biogas upgrading unit, at the moment we are in the final phase of getting the permit. And once we get the permit, most probably by the beginning of next year, the biogas upgrading unit will be installed as well. So this is the overall concept of case study 3. So we have the manure and agro residues from the farm, and they are being fed to the first mesophilic digester, and the digestate of the mesophilic digester is then being fed to the thermophilic digester, and the collected biogas. Some part of this biogas is being sent to the cogenerator, and the other part is being sent to the biogas upgrader. And from the biogas upgrader cryogenic process, we have liquefied biomethane and liquid CO2. So some part of the digestate and the liquid CO2 are then used to grow macroalgae and purple bacteria. And then the rest of the digestate is being transported to France. But in the next presentations, you will be hearing more about the valorization of the digestate and liquid CO2. The most important criterion in a biogas plant, of course, is to ensure a continuous feedstock supply. So to co-digest with manure, we seek for alternative co-substrates. And the first thing that came to our minds were, of course, potato waste, as is quite abundant in Belgium. But after a quick survey, we realized that it's not easy and definitely not free to supply potato waste to the farm because of the high demand, just like the other substrate feedstock in the region. In that sense, the owner of the farmer suggested to use the residual feed of the cows, such as yeast concentrate or corn cob, that is abundant in the farm already in huge piles. So we took manure, potato waste, and residual yeast concentrate, and we conducted preliminary batch tests, anaerobic digestion tests, to see their biomethane potential. As expected, potato yielded the highest, whereas the co-digestion of manure with potato waste and yeast concentrate were more or less the same, which was important for us because potato waste were kind of a reference to us. So then we decided to move on with yeast concentrate as a co-substrate. And the next step, we scaled up and we performed pilot scale anaerobic digestion test. We mimicked the same operating conditions of the farm scale. So we worked with 272 liters CSTRs, one mesophilic operated at mesophilic conditions and the other one at thermophilic at a hydraulic retention time of 28 days. So we first fed the digesters only with manure for 4 HRTs and then co-digested manure with yeast concentrate for additional 2 HRTs to see the performance in a continuous operation and also to see if there would be any process problems, operating problems. In the end, we saw that the co-digestion of manure and yeast gave 1.6 times higher biogas production compared to monodigestion of manure. We also observed as additional biogas recovery by the thermophilic digester as a post-digester, but also increased digestate quality. We also observed high hydrogen sulfide in the biogas, which was already a warning sign for us for the biogas cleaning step. So today, the farm digesters, the farm scale digesters on the farm are up and running. Around 80 cubic meters manure per day are fed together with 2 tons of corn cob mix. And we have a biogas production of 110 cubic meters per hour with methane in the range of 50 to 55% in the biogas. So, as expected from our previous experiments, we have high hydrogen sulfide in the biogas, even after the activated carbon. And to deal with this problem, at the moment, the farmer adds ferric chloride to the reactor to precipitate iron sulfide. But of course, this is an additional cost for the farmers, which we would like to avoid in the future. That's why we need to work on the cleaning step. And the final slides are on the biomethane, biogas and biomethane byproducts, which are digestate and liquid CO2. So we characterize the digest state according to the product's function categories of the fertilizing product regulation if it's compiles to be used as an organic fertilizer. So the key parameters like organic carbon, macronutrients, and micronutrients are well balanced in the digest state, and the metal contents are below the limits except for iron, which is as expected because we are adding iron to the reactors. That we will try to avoid in the future. And there were no pathogens detected in the digest state, and this is a requirement of the animal byproducts regulation to be transported into cross borders. And finally, we have food-grade CO2, which has a wide application in the industry. But here I wrap up my presentation and gave the floor to Andrea Munaretto, so he will be talking about the biogas upgrading units. Thank you.
Thanks. Share my screen. All right, can you see it? Good. So, as mentioned before, let's talk a little bit about the demo plane for the case study 3. And the demo plant will be installed in the dairy farm in Belgium. And the aim is to test an advanced cryogenic technology where we are supposed to convert biogas from manure into 2 streams. From one side, a liquid streams of biomethane, and the other side, liquid CO2, using a special process called cryo-upgrading. This kind of setup allow us to evaluate either very small plants, those processly roughly less than 200, 100 cubic meters of biogas per hour. In this case, actually are 50, can remain economically viable even without government incentives. We know it is a very ambitious goal, but it could greatly impact the profitability of small-scale biogas across Europe. Now, just giving a little bit of background, let's talk about reducing the carbon footprint, because we think it's a very important topic. In line with the goals of the Renewable Energy Directive, the directive basically aims to reduce emission by capturing CO2 for biomass, replacing fossil-based CO2 and promoting the use of biofuels. If we look at the table starting from 2026, the target is to reduce the emission by 80%, which is a pretty huge amount, but it means reaching 18.8 grams of CO2 equivalent per megajoule from biofuels used in the transport. And to reach that target, our focus is to produce renewable source with high quality, because it is directly linked with the carbon footprint reduction. Then we have to do it in a very efficient way. So we have to reduce energy consumption. And capturing CO2 from the biogas, replacing fossil CO2, means approximately reducing the carbon footprint by 42 grams of CO2 equivalent per megajoule. And these steps helps us to contribute in lowering the emission and creating clean energy solutions. All right, in the first stage, before going detail into the demo plant, during the first stage of the project, we created a test bench as a part of the project experiment with the goal of validating the concept. Basically, the test bench was designed to test the cryogenic capture of the CO2 in a biomethane stream, and in detail, the operation of the membranes, the operation of the cryopolish process, and testing 2 different CO2 composition, one of 20% and the other one of 1%. And the goal here was to achieve a CO2 level below 100 ppms, and the result was coherent and positive, confirming the expectations. Here we go a little bit more in detail on the demo plant. You can see here a rendering and some pictures of what we are doing. And based on the concept, we can divide the concept in three main groups. The first group, which is concerning the H2 removal, the biogas compression, and the dehydration, essentially consists of a filtration system. The first group handles the pre-treatment of the biogas, including removing impurities, compressing and dehydrating the biogas. And once clean, the biogas, which is mainly made by of water, CO2, and methane, goes through an heat exchanger and the cooling unit to remove the humidity, and then it is compressed. And finally, always in the first group, we have a PSA unit to absorb any remaining humidity and making the biogas free from water and ready for the liquefaction stage. Then if we jump into the second group, after the hydration, the biogas is completely dry, or it is expected to be completely dry, and it is sent to the group 2. And the second group is basically the core of the demo plant, and featuring an innovative unit called the sublimator. In very simple terms, here it is a heat exchanger containing a multitude of tubes and fins, which are properly sized and through which the refrigerant fluid goes, while outside these cooling tubes, the biogas cools down. The unit works as a sort of an heat exchanger where the biogas enter at the room temperature and exit at around 150 degrees. The system itself operates counter current, so it means that the biogas flows in one direction and the refrigerant in the opposite. And this ensure, or we expect that can ensure an efficient heat exchange. It's interesting to mention that during the testing, we have discovered an interesting phenomenon, which is the CO2 starts to solidify as soon as it touches the cold walls, even if the biogas is not fully cooled. And this allows basically to send the biogas directly in the sublimator. And after that, the liquefaction will take place in a dedicated unit, which consists in the group 3, where there through a closed ranking cycle, we treat what we get and we transform it in liquid form. The CO2 that is produced is expected to be food grade, in food grade quality, which is absolutely very important. And we are going to confirm that as soon as we have the startup of the plant, starting by the first quarter of 2025. And this CO2 will be used in the work package 4. Here we just would like to emphasize 3 main points. The first one is this is an optimized system to convert biogas directly into 2 valuable liquid products. One is biomethane and the other one is CO2. It offers being a sort of black box and an all-in-one solution to improve what we call TOTEX. So we have an optimizing of CapEx and OpEx cost. And of course, this reinforced the business case. And last, with the rising value of the renewable CO2, which is supported by the government as a substitute for fossil CO2, its price of the CO2 is expected to grow and increasing the value, and that also increases the value of the liquid biomethane and creating opportunities to sell certificates. So we bank a lot on the CO2 reduction. As of the main next step, so we are going to deliver, install, and having the startup of the demo plant by the first quarter of 2025. Then we also focus on the microalgae cultivation on the digestate, and the CO2 will be used in the work package 4. And then we studied toward further business case optimization by addressing biogas and biomethane subproducts with their cost and valorizations. That's all from my side.
Perfect. Thank you very much, Andrea. Okay. It's on CO2 valorization, and Georgina and Marcella will be the presenters. We are tiny bit late, but please go ahead.
Okay, thank you, Stefania, for the presentation. I will share my screen. I guess you can see the screen and you can hear me. Okay, perfect. So yes, Stefania said I will talk about the part regarding CO2 valorization from biogas streams.
Yeah. We see the PowerPoint. We don't see the presentation.
I don't know why I am sharing it.
Yeah, we only see the PowerPoint presentation.
Okay, let me try again to share.
Is it maybe in another screen?
Now?
Now. Perfect.
Okay. Perfect.
Great. Thank you.
So yeah, we'll talk about the CO2 valorization. In this case, from the liquid CO2 and the digestate from the biogas plants, we will be working on valorizing these streams through 2 different technologies. First, using photobioreactors for microalgae cultivation, and second, using fermenters to produce the one side biopolymers, and on the other side organic fatty acids through different microorganisms. So here we have a brief scheme of these processes. So starting with the part regarding the biopolymers and biochemicals through the fermentation technology from the carbon dioxide, we have here a brief list of the biochemicals and biopolymers we have selected. First, in the case of organic acids, we selected the caproic acid and succinic acid because of its expected market growth from now to 2028, and for having a wide range of downstream applications in the case of food industry, fuels, cosmetic, or the pharmaceutical industries. In addition, we can see that these biopolymers, the S.p.A, have similar opportunities and application in the industry, and also with a good market expect growth from now on. So here we have the microbial strains we selected to conduct these reactions. In the case of biopolymers, we will be use Cuprevidus necator, and we will use the CO2 as the carbon source and the digestate as the nitrogen and phosphorus source. So we will produce through a fermentation reaction PHA-rich biomass in which it will be further extracted to obtain the final biopolymers for different applications. And in a similar way, we will be having the production of volatile fatty acids through the selected strains, in this case, Megasphaerales deni and Actinobacillus succinogens. And in this case, we will also need to extract these volatile fatty acids from the fermentation broth to finally purify them and utilize them for different applications. So here we organize this process in lab scale experiments in which we test the microbial strain, which is the Cuprea virus negator, and the digestate, specifically the liquid fraction of the digestate. Here we have a list of the reasons why we selected these strains according to literature research. And here we have also a list of the operational conditions we selected to perform these first preliminary trials in the lab scale to test the substrate and the microbial strain. We used different gas bags with the mix of gas we needed to grow this microorganism using hydrogen, oxygen, and CO2 in a controlled environment. And we used also a shaker with different bottles to produce this reaction. So we can observe on one side the results with the synthetic medium, and on the other side the results with using the recovered digestate to produce these biopolymers. We can observe we obtain similar productivities, a bit higher in the case of the digestate, but at the end the content of the dry cell weight was higher in biopolymers in the case of when using the digestate. So so we can assume that the digestate is a good substrate source to produce these biopolymers through these reactions. So in a similar way, we use the same in the case of the biochemicals. In this case, we conducted different lab scale experiments using the selected strain to produce the succinic acid. We have also the list of the experimental conditions we followed, and here we have a picture of this lab scale trial, first in small serum bottles, and then with 1 liter bottles to perform this experiment. So here we have both the results when using synthetic medium or when using the digestate as the nutrient source. We can see the productivity is a bit higher in the case of the synthetic medium, but the final production at the end of the exponential phase was higher in the case of the digestate. However, it reached later on. And at the end, the concentration of succinic acid in this case was similar, but a bit higher in the case of the synthetic medium. However, the CO2 consumption seems to be higher in the case of when using the digestate. So here we have a brief summary. In the case of biopolymers, we obtain successful growth when using the digestate, but we can assume we have limitation in the gas mixture of gas liquid according to that we use these gas bags to perform these experiments. So we will need to have more efficient systems to improve these in the fermentation process in the upscale operation. And similarly, in the case of the succinic acid, we have preliminary data of these results when using this digestate, but maybe we have lower headspace over pressure in comparison to when we use upscaled operation. So the design of the pilot scale operation will somehow improve and optimize these reactions. So here we have a picture of the fermenter we will be using in a pilot scale fermenter of 50 liters to produce these products. We will have different proof to automatize these processes, to also to optimize the gas liquid mixtures and the gas pressure in each case. We'll have an automatic control unit to analyze the data and to adjust in each case the reactions. So we assume we can, following the results in the lab scale, we will be able to optimize the results that we obtain. Now moving in the case of the microalgae production from CO2 and digestate as an alternative protein source. Here we have a brief scheme of when using this liquid CO2 from case study 3 and digestate to produce microalgae biomass in photobioreactor. The idea is to obtain this microalgae biomass to be used as algae-based animal byproducts for feed. In this case, we have studied 3 different microalgae strains: Chlorella vulgaris, Parachlorella kessleri, and Tetradesmus obliquus, all selected according to literature because being accepted as consumption in the European Union for having a high protein content and to be using formulation of feed and having good digestibility. Also for having efficient CO2 uptake according to the upscale that we are using in this case. And also we have evidences of that we can obtain higher biomass production using these photobioreactors. So in this case, as in the other part, we perform different first lab scale trials, and second photobioreactor operation. We have studied different microalgae strains and also different types of digestate from different origins. To analyze how it is better to cultivate this microalgae. The activities conducted in the lab scale have focused on evaluating the influence of the strain of the type of the digestate and to acclimatize the microalgae at increasing concentrations of nitrogen, or in its case of digestate. Here we have the list of the operational conditions we perform in the lab scale trial, and also comparing the synthetic media and the liquid fractions of digestate. Here we have an example of comparing the 3 strains when using the synthetic medium and the digestate. We can see in this case that the productivities seem to be higher when using the digestate as the nutrient source. And however, the protein content, the results obtained are similar when using both media. Having these results into consideration, here we have the summary of the design of the pilot photobioreactor that we will be using to upscale this operation that we first test in the lab scale. We'll be having a pH control by CO2 addition, also a temperature controller. We have a proof for pH, temperature, CO2, of dissolved oxygen, and turbidity. And we can also analyze the light intensity in line. The harvesting method here is by centrifugation, and we have also a control unit to analyze each parameter of the process. Here we have a brief summary of the the pilot operation we will be having. We have started working with Parachlorella kessleri as the selected strain. What we want to do is to validate in the pilot scale the production of this microalgae using this CO2 and digestate, and to optimize and maximize the production from the lab scale results to the pilot scale. Also in a way to validate this production and this technology as to obtain alternative protein source using not only synthetic but also liquefied CO2 and digestate from the case study 3. Here we have a brief preliminary result of the pilot scale operation when using the synthetic medium. We can observe the batch phase and the continuous phase in which we harvest culture each day. Here we have the productivity during the batch phase period, and also the maximum biomass production was 856 milligram of volatile solids per liter, with an average biomass productivity of 37 milligrams per liter per day. In the case of the digestate liquid fraction, we can see that we have a lag phase of 7 days, with, however, a similar biomass productivity during the exponential phase. But when we started the continuous phase, we obtain slightly high, lower biomass production, with an average biomass productivity similar to when using the synthetic media. So the findings are that we obtained successful microalgae cultivation from CO2 and from digestate in the lab and also in the pilot scale. We need to optimize the growth performance with the digestate. However, we obtain similar results to when using synthetic media. So at the end, we will be able to continue working with the recovered CO2 and the digestate from the biogas plants from the case study 3. And now I pass the floor to my colleague, Marcella.
Thank you.
I need to stop sharing. Okay.
It's fine, I'll take over. Okay, you see everything fine? Yes. Okay, good. So thank you, everyone. I'm the last one, but I'll be brief. So given the positive results we had in the experiments conducted at Beta, we did some preliminary calculations on the potential of growing microalgae at the Belgium pilot. So if we would install a microalgae facility in our case study 3 here in Belgium, how much microalgae could we actually produce? So just a recap of the Belgium pilot, it's foreseen to process 25,000 tons of manure per year, which means that we have a production of around 23,000 tons of digestate per year and 845 tons of CO2 per year. And we talked to the farmer, as my colleague Çagri explained, there is excess digestate that is being produced that cannot be land applied in the farm. So this is expected to be 15,000 tons of digestate per year that needs to be either treated or exported or can be used for microalgae production. So how, if we use this digestate, how much algae can we produce? So the first calculation we did was about the nitrogen content. So with 15,000 tons of digestate with a nitrogen content of 0.51%, this data is directly from our pilot. We have 87 tons of nitrogen being produced every year that we can use as an axis. So we know that microalgae, depending on the species, can have up to 7% nitrogen in their concentration. Most of the commercial algae are around 5 to 7%, so we're using the higher concentration of nitrogen. So we can have a production of 1,200 tons of algae per year, which sounds quite nice. I will put in perspective this number soon. So we did also the same exercise for the CO2 balance. So from our case study 3, we have 845 tons of CO2 being produced per year. We know that to produce 1 kilo of algae, we need 1.8 kilo of CO2. This means that we can produce 460 tons of algae with this CO2. So from here, we already have a perspective that the CO2 is our limiting resource in the dairy farm that we are considering, but still we can produce quite some algae. So hold this 460 tons of algae per year in your mind, and then let's see how this compares with the current production. So the current algae production in the EU is 182 tons per year of microalgae. This is divided between several of the EU countries. You can see in the graph here, there was a survey in 2022. Very interesting seeing all the algae companies in the EU. We see that we have less than 50 companies producing algae in the European Union at the moment. So it's still a sector that is in its infancy, and now that there is some incentive, is slowly growing. So you see that only with the resources of one dairy farm in Belgium that we are considering, we can already produce much more than the current algae production in the EU, showing that there is quite some potential to transform this algae production into a sustainable process by using recycled nutrients. So how do we see this integration of the algae production in the dairy farm? So I did a calculation for the 460 tons of algae that can be produced using the whole CO2 from the pilot. We have an algae production of around 100 tons per hectare, which means that we will need 4.6 hectares in the farm for the algae production. It seems okay if we consider it's a 150-hectare farm. However, when we put into the perspective that the biggest algae facility producing algae in the EU at the moment is a 2-hectare facility. So now if this dairy farmer suddenly wants to produce all the algae that he can with the nutrients that he has, he will become the biggest algae producer in the EU. So this seems like maybe not the best scenario for this dairy farmer. So what we propose is that this is a very good opportunity to couple and make an industrial symbiosis, so that an algae producer that is willing to do the investment to install such a big facility with all the reactors and all the equipment that is needed would build his facility near this dairy farm, so near the source of nutrients, and capture the CO2 and the digestate from the farm, and then he would have a very sustainable process and possibly also economically viable with this symbiosis of a win-win situation for both industries. So there is quite some potential of coupling algae production with a dairy farm with anaerobic digestion and the upscaling of the biomethane. So there are some there is some interesting numbers there to be considered, and we hope that this will pave the way to the future of the technology. So yeah, that was it. Thank you.
Thank you very much. And thank you everyone who is still watching us. And we're a bit over the limit, 26 minutes over the limit. So let's just make it as fast as possible. We have a bit of time for the Q&A session. Maybe 5-10 minutes stop. So from the people in the audience that have your moment. Please type your questions in the chat in case you don't want to do them directly. And I will just ask, I think all of the presenters now have their, maybe all of the presenters can have their cameras on so that they can make the questions directly. So we can open now the discussions of the Q&A. Maybe Laia, you have a question.
Yeah, there are questions in the Q&A.
Perfect. I'm sorry, I didn't got the notification. Okay, so from Joao de Santos, in case study 3, is it economically viable to transport the digestate around 90% of the liquid fraction from Belgium to France? How much kilometers are we talking about? So maybe this is a question for, yep.
Yeah, sorry. That one at the moment, I don't know. We still have to see because at the moment it's not being transported. So that one we will be investigating in the future.
Okay, so this is a point for
it's in the
future.
border. It's not so it's in the border of France and Belgium. So it's not south of France, let's say. But we will see the feasibility indeed. Yes.
Okay, perfect. And also from Joao, in case study 2, just to remember that we don't have the case study 2 expert. Why are we using pyrolysis and not gasification if the goal is to produce more syngas biomethane to get injected to the grid?
Yeah, so it's a very good question. I have it also too. Like I cannot answer you because my logic would say the same. But I guess it has to do with the composition of the syngas you get, that you want to have more hydrogen. So this hydrogen then can react with the CO2 and produce the biomethane. I guess this is the reason. But Arthur should be here and tell you the answer. This is what I think is the reason.
What we can do, Joao, for your 2 questions, maybe we can, we have your email, so we can send you the answers once they're done. Once we have the answer, but I mean, for the first one, we still need to figure it out, but we can definitely send this to Arthur or to BA, and probably they can give you a more straight answer. Then we have a question from Marcos Machado. Georgina, thank you very much for your presentation. In my bachelor thesis, I'm working on the usage, oh wow, she's real. I'm working on the usage of anaerobic digestate as a nutrient source for microalgal growth. I would like to know if your work, the liquid fraction of the digestate, is somehow pre-treated before it is fermented or used in microalgae cultivation. And is this pre-treatment cost effective? When choosing the pre-treatment method, do you mainly consider the reduction of contaminants in order to improve the extraction process? And finally, you said that you control the pH by adding CO2, but you have tried cultivation without the pH control? I know there's a lot of questions. I don't know if Georgina, if you open the Q&A, you can also read it.
Yeah, the first part, we have worked with different kind of the liquid fraction of permates. One was filtered through a membrane process, but we also work with one without filtering. It was only like after the solid liquid separation. We also tried to use it. In the case of the fermentation studies, was this fraction of the digestate, the liquid fraction. But in the case of the microalgae, it was always with the, well, in 2 cases, we tried with the membrane filtration test, and in the other with only directly the liquid fraction. Yeah, somehow we reduce a lot the pathogens and also the turbidity of this digestate, but we should also, as you commented, consider the price that this separation represents to the final all the production cost. And the second question of the pH controller, well, we somehow managed to work for a couple of days without the CO2 adjusting the pH. But at the end, the microalgae didn't grow during these days. So I guess it should be interesting to try maybe to combine different periods or different hours when using CO2 addition by pH control, or maybe combining with no CO2 addition. But without any CO2, I don't think the microalgae will be able to grow because they won't have the carbon source. I don't know if I have somehow answered the question. I tried to go really fast, so.
Marco is answering on the chat. Yeah, thank you. Okay, perfect. Anyone else has any other questions? I don't see anyone typing in the chat or the Q&A. Okay, perfect. So this would be the end of our bio-impact webinar. And thank you all for your participation, and thank you, Marcos and Joao, for your questions. We hope you found this webinar useful, and if you have any other questions in the audience or you need any more information, please reach out to us. We have a webpage, we have LinkedIn, Facebook, and X platforms. Look for us as a SEMPRE-BIO project or SEMPRE-BIO, most of them. The website is SEMPRE-BIO project. I think Marco just typed something. Oh, I love it. Thank you. Thank you, Marco. Okay. So thank you, everyone. Thank you for the presenters for your time too. And we'll see you probably maybe in another of SEMPRE-BIO's webinars. Thank you, people. Bye.
Thank you. Bye.
Thank you.